Hi XR developers! Today I'm excited to show you how to install and use Unity Sentis, which allows us to run AI models directly through our Unity runtime on our standalone devices, which opens up a huge variety of use cases. I will show you how to import your own AI models in the ONNX format. We will take the MNIST model, which is a famous model for detecting hand-drawn numbers. We will create our own input for that model by drawing numbers on a texture in Unity by simply using our fingertips. We will use the Meta XR SDKs for that. We will feed that input to our model, and our input will run through all the layers of the model until in the end we will get an output. This output we can use for our gameplay. In our case, we will just show the results in the inspector and you will see which number the model predicted. If you enjoy this type of videos and they are helpful to you, please take a second to like and subscribe to this channel. And please consider supporting my Patreon, where you can find all the source code for each tutorial. If you have any questions, feel free to join our Discord community, where we are happy to help you. And now, let's get started with Unity Sentis.
In games, there are some unique problems that are difficult to solve with traditional code, and neural networks are a great way to solve some of these problems. Now, Sentis is a great tool because traditionally, neural networks are written in Python, which is not compatible with Unity. They also run on cloud infrastructures and are usually not at all optimized for the use in games. To use Sentis, it helps if you have some experience in using machine learning models, for example, in a framework like TensorFlow or PyTorch. Alright, now let's look at how the Sentis workflow is supposed to look like by setting up a simple script. Let's start by installing the Sentis package. We can simply open the package manager and type in com.unity.sentis. This will install the latest version in your project. After installation, we also have the option to import some samples. These samples will teach us different things, such as how to encrypt a model, how to read output asynchronously, or how to run a model. Feel free to take a closer look into these samples. Also, if you would like to get entire sample projects, you can find a link in the description to Unity's GitHub repository, which has some great projects, one of which is the digit recognition sample, which inspired today's video. Let's continue by downloading our desired MNIST model. We use this GitHub link where you can find different versions of the model. The link is, of course, in the description as well. We will download the MNIST 12 model. Let's then create a new models folder inside the assets folder and import our model. Sentis will then automatically try to make the model smaller and more efficient by removing or replacing layers or subgraphs and setting the layer to run on the CPU if necessary. Then we download a texture that has a number written on it from the Unity Sentis documentation page, or you can also find a Google Drive folder in the description. Place it in a folder you want, for example, a textures folder, and then let's create another folder called scripts. And let's create our first script called something like classify handwritten digit. This script will load and use our model to classify the texture and provide us with an output. Now, let's go step by step with a very basic setup of Sentis. We first use the unity.sentis namespace. We then would like to declare 3 fields that we can see in our inspector. One will be where we reference our model, another one where we reference our texture, and a third one will be an array of floats which will show us our results. We then declare 3 private fields. To run our model on our device, we need to create a so-called runtime model. For this, we declare a private field of type model. Then, very importantly, we create a worker. In Sentis, a worker is the inference engine, and it is created to break down the model into executable tasks, as well as run the tasks on the GPU or CPU and output the result. Lastly, we create a private variable of type TensorFloat, which will be our input, or in other words, our texture. The next step is to load our model, which we usually do in the start method. We can simply call the model loader from our model variable and assign the MNIST model we later reference in the inspector. Then, we create our worker with GPU compute backend. The GPU then queues the work to be executed in the correct order. To know more about all the different backend types, check the link in the description. Next, to keep our code clean and clear, we create a new method called executeModel, where we have the logic that actually runs our input through our model and gives us the output. We start by checking if there is still some previous input running. If so, we want to dispose of it. Next, we create our input and convert the texture into a tensor, which can then be sent to the model. Here it is very important that we specify the width, height, and channels of the input. We can find this information by clicking on our model in the Unity project and checking the Input tab in the inspector. In this case, the width and height is 28 pixels, and the channel is 1, which means black and white. Then, the worker can finally run the model with our input by calling the execute function on our input tensor. We can then receive the output from our model by calling the peak output method from the worker. Unfortunately, however, we cannot really read the output yet. For this, we have to call the make readable method from the output and also show the array of outputs in our results. After using the output tensor, we can dispose of it. Lastly, to keep our code clean and save our hardware resources, we tell the GPU we're finished with the memory the engine used by disposing of the input tensor and the worker in the onDisable method. Fantastic. We can now go back to Unity. Add the script to an empty game object in our scene and reference our model and texture to it. We are then ready to give this a try. As you can see, we get 10 results, which is equal to 1 result per number from 0 to 9. But somehow we are getting a value that we can't really work with in Unity, and we don't really see right away which number was detected on the texture. So, let's find out how to change that right now. To get a different output, we need to modify the layers of our model. For this, let's add the unity.sentis.layers namespace, and in the start method, we would like to add a new so-called Softmax layer to the end of our model and modify the output to be a Softmax output. Adding a Softmax layer to a neural network model transforms its raw output into probabilities, indicating the likelihood of each class. This change makes the model's output more interpretable for classification tasks, as it clearly shows the predicted class with the highest probability. Let's give our script another try. As you can see now, number 7 has a probability of almost 1, which indicates to us that our model has interpreted our input texture as a 7 and is 99.9% sure of it. Amazing. But this wouldn't be one of my usual tutorials if I wouldn't give you an XR use case with it. So let's now build an experience where we draw on a texture and then feed it to our model. Let's make sure we have the Meta XR SDK installed first. Then in our classify handwritten digit script, we just have to make a few changes. We would like to get rid of the input texture, and for our execute model method, instead use a texture 2D parameter, which means we will receive our texture from another script. To execute the model and call this method from another script, we also have to make the execute model method public. So, let's create this new script that is creating our new input for us by drawing on a texture by using our OVR hands. We are not going to cover this script in detail since it isn't really part of the Sentis tutorial. It is just a simple drawing script I created to draw some textures that we can send to our model. We want to draw on an image, so we need a reference to a raw image. We also need a reference to our digit classifier script and a reference to the transform of our fingertip, which we can later easily assign in our inspector. We then want to introduce some amount of delay, which is used to wait for the texture to be sent to our model. I decided to do this because when people are writing, they usually lift their fingers or pen shortly and continue to write. In that short time, I don't want to send the texture yet, because maybe we haven't finished drawing yet. So we will wait for 1 second after we stopped drawing until we send the texture. In the script, private variables like hasDrawn and lastDrawTime are used to track the drawing status and the time of the last drawing action. The script accesses the main camera of the scene to convert the fingertip position into screen coordinates, facilitating the drawing on the raw image. The drawing is realized by modifying pixels on a texture 2D object, drawing texture, which is displayed on the raw image. The script includes functionality to clear this texture, effectively resetting the drawing space. In the start method, we want to create a new texture, and let's make sure we have the same dimensions, like we had for the input of the model, which is 28 in height and width, to get more accurate predictions later. In the update method of the finger drawing script, the logic primarily focuses on detecting and responding to drawing actions. At each frame, the method checks if the user is drawing by measuring the distance between the position of the fingertip and the position of the display image. If this distance is less than the distance we set in the inspector, It's assumed that the user is touching the image and actively drawing. When a drawing action is detected, the method first looks for an existing coroutine, check for send coroutine, which is responsible for sending the drawing data after a delay. If this coroutine is already running, indicating that a previous drawing action was in progress, it is stopped. This reset ensures that the delay before sending the drawing starts anew from this moment of drawing. Next, the method calls the draw function, passing the current position of the finger. This function translates the physical position of the finger into screen coordinates and updates the drawing texture accordingly, effectively rendering the drawing on the raw image. The script sets the hasDrawn flag to true and records the current time in last draw time, indicating that a drawing action has taken place and noting when it occurred. If no drawing action is detected and the hasDrawn bool is set to true, the method checks if the time elapsed since last draw time is greater than the delay to send period, and if the coroutine is not already running. If these conditions are met, it starts the check for send coroutine. This coroutine waits for the delay to send period and then triggers the execute model method of the classify digit script, effectively sending the texture data for processing. Finally, we have the clear texture method, which allows us to clear our texture after the model has processed it, so we can draw a new number once again. We will call this method from inside the classify handwritten digit script at the end of the execute model method. And that's it, guys. Let's set everything up in our Unity editor. We add our new script to the same game object and reference the both scripts on each other. Next, we use the building blocks from Meta and add an OVR camera rig, hand tracking, as well as synthetic hands to our scene. We then go to our right synthetic hand and look for the tip of the index finger. We can simply drag it into the fingertip marker transform field. Lastly, we need an image that we will draw a number on, and that will be our input texture. For this, we add the pokeable item building block. This already adds a poke limiter to our synthetic hands, which prevents them from fading through buttons and other poke interactables. We can see that by clicking on the dependency on the building block component. As you can see, we need 3 references there. A reference to the hand itself, a reference to the poke interactor, which was also automatically added for us, and a reference to the synthetic hand. On the pokeable item, we can remove the button visuals and instead add a canvas. We set the width and height to 1 and the scale to 0.1. Then we want to move it slightly forward on the Z-axis to make the hand visuals collide more accurately with our image. We then add a raw image to the canvas and also set its width and height to 1. Lastly, we reference this raw image on our finger drawing script and finally give it a try. As you can see, we can draw a number by using our right index finger, and we have the freedom of drawing, shortly lifting our hand, and then continue drawing. If we completely stop drawing and wait for a short while, we will send the texture to the model, and we can then see the results in the inspector. We can see that the results are extremely accurate, 0.99 and so on, indicating our model is more than 99% sure of its prediction of the number, and as you can see, it is predicting each number we write correctly. It's important to keep in mind that you will get a number between 0 and 1 and can mostly ignore the other values. You could even write some logic to only output the number with the highest probability, which I did in my own application.
Alright guys, and that's it for this video. I hope you learned a lot. Please, again, take a second to like and subscribe to this channel, consider supporting my Patreon or join our Discord community. As always, you can find all the relevant links in the description. Let me know what you want to see next, and I see you in the next video.